invariant thing was super confusing.
What was confusing?
The invariant, like when we were like the theta for A and theta for B, and you said like since we're not changing the coordinates, so the theta for A is still like invariant from like the B one. So I was thinking like if there's another coordinate system C, so like you change from A to C perspective and B to C, then which like theta to use?
So if I could paraphrase your question, the question is you have a theta. You have this line elements for it. Why is the number that comes out the same for everybody in that space-time? That's the question. Right? So you would ask one person, what is the amount of time? And he will say 4 seconds. Why is the answer not the same 4 seconds for everybody else? Because if we made a whole point in special relativity and also in the beginning of this course to say that d taus are invariant, right? Yet here I explicitly made use of the fact that I could calculate the d tau for one person and the d tau for another person, and they were certainly not the same number. You would divide it by each other. You would have your general time dilation. And I think the question is, how does that happen? I mean, shouldn't d taus be the same for all or something like that? Isn't that what invariance means? And the answer is no, that's not what invariance means. Invariance means if you go to some other guy's coordinate system, if you would go from one guy's metric to some other guy's metric, then that number should be the same.
You're still talking about the same event,
Yes.
just
So does
different
this mean
observers.
If you change like a coordinate system, the two proper times will be exactly the same
Yes.
No, but that
in
was
whatever
my question,
coordinate
though.
system you go.
So like, because over here it's like this A and B, but like if we go to some other coordinate system C,
It's not another coordinate system, it's the same coordinate system, but you're at a different location in that coordinate system.
Yeah.
I know, I
That
mean
is
like,
confusion.
because then if you put this as the origin, then that's the.
No, but you're not allowed to. What the origin is defined by your metric tensor.
Okay.
So you are at different locations
It's the
in
map.
the same coordinate system, but you're not changing coordinate
So
system.
the center of the black hole is the origin.
It's the origin of the coordinate system in TR theta phi coordinates. That was the point that I tried to make when somebody asked me this during the main lecture. I said, well, do you see that nobody's going from T R theta phi to T prime R prime theta prime phi prime? You're all staying in still coordinate system. You might be at different locations in that coordinate system, but you're in the same coordinate system. Now, there's no rule in relativity that says d tau should be the same at every location in a given coordinate system. Only that if you would go to another coordinate system, then that number would be the same. We're not going to another coordinate system, we're staying within this one. So this is why the d tau should not be the same. Now, I had an interesting discussion with Giovanni during the break between the main lecture and the tutorial, and that was, well, I'm paraphrasing the discussion a little bit here, but you might have noticed that during special relativity we never worried about in what location you were in a given Minkowski spacetime, right? You had a Minkowski spacetime, and you went to some other guy's coordinate system, some other guy's Minkowski spacetime via Lorentz transformation. You went from x, y, z, t prime, to x prime, y prime, z prime.
You were normally at the origin, right?
Yes.
Because if your coordinate system is moving,
Yes,
you're
but you
moving
don't
with it.
necessarily have to, though.
Yeah, you don't
I
have to.
mean, what I could also do is define a coordinate system around me where I happen to not be in the origin.
Yeah, x equals something.
Sure. That doesn't really matter though in Minkowski spacetimes, because Minkowski spacetime looks the same at every location anyway. So it doesn't matter where you put your origin. If you've defined your coordinate system with the t, x, y, z, you can sit wherever in that coordinate system. You would still measure the same d tau. If you go to some other guy's Minkowski spacetime, you would still measure the same d tau. That second transformation is what is defined by invariance. The fact that within, so even if you don't go to some other guy's coordinate system, you say within your coordinate system, but you move in the coordinate system, you don't sit in that coordinate system, but you move to some other point in that same coordinate system. The fact that that is the same d tau, that is due to the fact that it just so happens that Minkowski spacetime looks the same everywhere. So let me make a drawing of this. I mean, I'm maybe just hammering the point home a little bit too much right now. But suppose that I have two Minkowski spacetimes here. Okay? Here's t, x, y, z, and this is t primed, x primed, y primed, z primed. And as you know, these two have a relative velocity of v with respect to each other. if you would measure some d tau in this coordinate system and you would ask this guy how much d tau there is as seen from his coordinate system, he would measure the same d tau. Fine. This is meant by invariance. Good. Now, what I could also do is completely forget about this second Minkowski spacetime. I'm going to look at this d tau, but see by two people within the same Minkowski spacetime. So one guy happens to be sitting here, could be the origin, and some other guy happens to be sitting here. Same Minkowski spacetime, same coordinate system, just different location within that. If you were to ask this guy how much time there was between two events, he would say d tau. This guy would also say d tau. Yes. This is not due to invariance. Going from one coordinate system to the other and then finding the same d tau, that is invariance. Being in the same coordinate system and still measuring the same d tau is because this particular coordinate system happens to have no spatial dependence. Contrast that please with your Minkowski or your Schwarzschild spacetime. Here's your black hole. Possibly here's another black hole. Or it's the same black hole maybe, but viewed from some moving coordinate system or something like that. You would measure something here, you would measure d tau. You would go to some other guy's coordinate system and you would ask him, there's no black hole here, here's where the black hole is. You would ask this guy about the d tau. He would also say, yes, that's still the same d tau, that's invariance.
Mm-hmm.
Forget about this one. In everything that we've done today, we have not introduced some other coordinate system. Everything we did from the same coordinate system. Now, if you now ask a person who's standing here versus a person who's standing here what the d tau is, they will not give you the same answer. That's not because of a lack of invariance. Invariance has nothing to do with it because we're still in the same coordinate system. This is because it so happens that the Schwarzschild spacetime has a spatial dependence. Things really do look different at different locations, so you get different d taus out of this. So you see this, there's two ways that the d tau can be the same. Either because you move to some other guy's coordinate system and invariance tells you that it is the same. One other option is you stay within one coordinate system, one metric space-time. But it just so happens that from this location to the next location d tau did not change. That is a different reason why d tau could end up the same. Now, we explicitly looked at the situation where we only stuck to one space-time, completely defined its origin by the black hole, but we did our physics from different locations within that space-time. That is what changed the d tau. Does that clear up things?
Yeah.
Okay, good. Now, let's do some fun exercises.
Sorry, then one more point.
Yes, go ahead.
Then why we bring this up? Where exactly in the exercise when we did in the lecture did you drop the word invariance, and why?
I didn't. Somebody did.
Oh.
In his or her question, I forgot who it was.
Okay.
The question was like the d tau A and d tau B.
Yes. Yeah. I mean, right now it was you.
Yeah,
So Sean asked,
Yeah.
why is it that we could use d tau A and d tau B to begin with? Doesn't it break the idea of invariance? And now the answer is no, it doesn't.
Okay.
What
So
room
it's-
number is this? Teresa's looking for us. Is this 343?
3.4. Yeah, that's
Yeah.
true. Yeah.
Yeah, I just told her.
Okay.
3.43.
Wait, so
Oops.
quick check. The second picture is
2.043.
basically time dilation due to the original space time, right?
Yes.
Okay.
Yes.
Gave my question in the lecture as well, but I think you kind of answered it as well.
Okay.
Special relativity, I mean, the time dilation due to someone's speed is already embedded.
It's
In
already
general.
built into the Schwarzschild space-time, so you don't have to by hand put that in. It will automatically come out. And to make it specific, it's the minus in front of whatever is in front of the dt squared, that minus, compared to the pluses in front of the other dr squares and everything. That is what gives you a time dilation. In fact, our first exercise that I would like to do interactively with you is discuss a little bit the properties of this Schwarzschild space-time. Because I just dropped it on you, I just said, well, here is this thing, and some guy calculated it. By the way, I didn't tell you the full story, right? I told you that he wasn't actually the first person to derive this Schwarzschild solution. He was the second, but he was the first who got it published. There's some karma involved here. That is that Schwarzschild actually derived this equation in the trenches of the First World War.
What?
Actually, I was sitting in some bunker doing physics apparently.
Whoa.
That's Teresa, I think.
Yeah.
Come in.
Go in. Hi.
Sorry, we forgot to tell you.
I'm sorry, there was some ad hoc changing at the last minute. People were not looking forward to being in this very stuffy, small room.
Yeah.
And unfortunately, Schwarzschild actually passed away from the First World War. I think he got shot and got gangrene or something like that.
Yeah.
So he never got to see his discovery in action as a free man.
Flourished, yeah.
Yeah.
I mean, the
That's
Schwarzschild space-time and everything is now a staple in general relativity.
Yeah.
Not
That's
just
kind
because
of
of its easy, relatively easy, calculable effects, but also because it's quite ubiquitous, right? I mean, the only thing that you need for the Schwarzschild solution to hold is a spherically symmetric mass distribution. Well, in astrophysics, almost everything up to good approximation is spherically symmetric. Not everything,
Yeah.
but a lot of it is. So
Is that the only exact solution we have to the Einstein field equation?
no,
or are there
no,
others?
there's many more.
So since he found that one,
Yes.
many others have been
Yeah,
found.
yeah, yeah. Well, not many others, but others. Yes.
But not for spherical masses. For what kind of distributions?
Well, there's not one of them for spherical masses, but
Rotating.
rotating.
Ah.
So they're spherical in mass distribution, but they have different moments in time.
Oh, okay.
That, if you will, is an extension of the Schwarzschild solution, right? Because if you take that solution, it's called the Kerr solution, and you take
Yeah.
time to zero, or you remove all time dependence, you should get back the Schwarzschild solution.
Yeah.
You do. Yeah, and there's more. There's the wormhole solution. That's right, the one that tells you that you enter here, you exit somewhere else in the universe. It's a different time, maybe.
Yeah.
There's the Alcubierre drive. I was just mentioning Star Trek because Star Trek is objectively a better series than Game of Thrones.
You're not informed to make that judgment.
And anyway,
I'm
Picard.
about to walk out.
So, as you might know, in Star Trek, their spaceships, they use something that's called warp drive. They have impulse engines. That's just Newton's third law. You push yourself away against something, so you accelerate. That's how all of our motion, as far as we know, works for masses. You have to push yourself away. Conservation angular momentum of a normal momentum. But in the series, you also have something that's called warp. That's when you start going faster than the speed of light. But is that impossible? No. According to the series, it isn't. Because around the ship, you have this bubble that itself, within that bubble, the ship is not going faster than the speed of light, so you're not breaking relativity. But the bubble of space-time itself moves through its surrounding space-time higher than the speed of light. That actually is allowed by general relativity.
Space-time can move through space-time.
Yes.
Mm-hmm.
And you make that bubble go faster than the speed of light. And now a beautiful thing happens. Star Trek was first broadcast in the 1960s. The series that I like to watch is from the early 90s, for sure. In the 1960s, they just had this literary device to explain how people could travel through the universe. And it turns out that in the intermittent time, general relativists have actually found a bubble solution to the Einstein field equations that allows this. And it's called Alcubierre, the Alcubierre space-time, Alcubierre metric. And colloquially it's called the warp drive metric. And in your Hartle book, actually, they have a small little box on it too, so you can actually see that if you want.
And how would you do it?
You would need to, here's where the crappy part comes in. So what people did was to say, well, suppose that you want to get some warp, Star Trek warp-likey drive. You would like to have this bubble that itself goes with the speed of light or faster than the speed of light. How would that metric look? Put it into the Einstein field equation and then deduce what kind of energy momentum you should have put in. Usually you do it the other way around. You save the energy momentum, you get back your curvature of space-time. Now they said, well, we want this curvature of space-time, what kind of energy should we put in?
Yeah.
The sad answer is that you need an enormous amount of it, energy, and the second part is it has to be negative. What? Negative energy.
Ah, yeah.
And it don't be negative in the sense that you shift your 0 point of energy, real negative energy. Objectively negative.
How is it possible to have like real negative energy?
To have what?
Real negative energy.
Well, you can in quantum mechanics. Yes, because of Heisenberg, you can have small amounts of negative energy.
Okay.
You need a lot of it.
Yes, so that's difficult.
For short amounts of time, right?
Yes, And
Yeah.
that is the crappy part. You can get your negative energies from quantum mechanics, but the pragmatic difficulty is that you need a lot of it.
Yeah.
So it's fun to know that this Star Trek drive actually is in principle possible if only we found the right energy source. So
I actually did a presentation on it during the core course, like presentation
Oh,
thing.
Yeah, I remember.
Really?
Do you remember? It was
Yeah.
on Warp Drive. Yeah.
Yeah.
did somebody give a presentation on that?
Yeah.
Well, it was like a 5-minute one, so not really significant, but yeah.
Oh, that's pretty cool. Sorry, in what context was it?
It's just the core courses. You have to
The-
give a presentation on anything.
The presentation skills course.
Yeah. Okay, wow. You remember who it was?
Me.
Oh, you
I'm
gave
saying
the
I gave
presentation.
it.
Oh,
Yeah.
sorry. Oh, okay.
Yeah.
So you knew what I was saying. You
Yeah.
heard this before. Yeah. That's
But they were saying in the literature that I read at the time, you need also something sort of like negative mass to cause the negative energy, something to
yes.
bend the bubble outwards.
Yes.
instead of-
That is the thing. Energy and mass is sort of the same thing for relativity. So, but yeah. So this is all to the question: is the Schwarzschild solution the only known solution? No, there's more. Some more exotic than others. But now, just to make things a little bit more difficult, this idea that you have that mass tells space how to curve, and then the curvature of space tells mass how to move. That sounds a little bit too simple because there's an interaction between this. But if you have a moving mass, it itself will curve space-time around it. So that means that whenever a little bit of mass has moved due to the curvature of space-time, it will also have moved the curvature around. So you have to constantly switch between the two equations back and forth to get the full answer. And that is highly non-trivial to do that exercise. So, okay. What I would like to do is interactively look a little bit more at the Schwarzschild solution. Let's pretend that we had never heard of the Einstein field equation. And we were to guess what the write it down first. And we were to guess, this is completely wrong, I'm sorry. Yes. So we can R. Okay. Suppose that we were to guess some curvature of space-time that will tell us something about gravity around spherically symmetric masses. Now, I subject to you that this is a good guess. And I would like to hear from you whether you concur. Pretend you've never heard of Schwarzschild. How would you argue that this might be a good choice for the curvature around a spherically symmetric mass distribution?
Can we assume that there's some kind of like general relativity time dilation and general relativity length contraction because of those?
You don't even have to assume, it's there, yes. So,
That's why there's like something like next to time and like
yes.
length. I guess.
Because without those effects, this would have been one and one more one, right? Because the fact that this does not say just one, and this does not say just one, tells you that there must be some strange effects in, well, at very least in radial distances
Yeah.
Yeah.
Exactly.
and in times. So yes, if you already know that you're looking for something that gives you some sort of time dilation or contraction or whatever it is, make it more towards the cookie. Then yes, you would probably be well off taking this guess. But why this particular form though?
Well, it's inversely proportional to radial distance and directly proportional to some quantity which we don't know. But it makes sense that it would be stronger the closer you are to the source.
I think it's pretty good. So you're saying, probably paraphrasing here, but you are saying that whatever effect you might have to this spherically symmetric mass distribution, you expect it to become stronger the closer you get to the thing.
Yes.
So in other words, the further away you are, the less you will see of it.
Yep.
So whatever contribution you bring should be something that diminishes as r becomes big. And we actually saw that during the lecture, that this actually becomes Minkowski spacetime in spherical coordinates at infinitely far away. So that certainly agrees with what you would expect for curvature around the mass, that if you're very far away from it, you will feel very little gravity. Okay.
So that's similar to saying that it's a radial influence, right?
Mm-hmm.
Okay.
Yes, but it's a little bit stronger because it says if the radial influence goes down,
Yeah.
you see, you notice less of it the further away you are. Just like gravity, by the way. So, okay, why 1 over r? Why not 1 over r squared? That works too. Why not instead of 1 minus k over r? Why not make it 1 minus e to the power minus r? That certainly goes to 0 at infinity. So why this particular choice? Why something over r?
Actually, probably would have guessed r squared first because that's more close to Newton's gravity. So I don't know.
Maybe it has to do with the units? No.
Well, the units are somewhere in k. But there's a unit question, I very much agree. But units will not change your r dependence. So there's I heard a nice suggestion here. Namely, well, you would expect it to sort of be like Newton-ish or something like that. Newton's gravity goes to 1 over r squared.
But this is more like the potential energy.
Yes.
Help me.
You want me to go further?
So I have a mouthful of cookies. I cannot
Okay,
I was
so
about to say, like, kind of what you were saying is usually in Newtonian mechanics when you're dealing with how much you need, escape velocity to escape a field or something, you usually deal with the potential of how much you need to pull something away for the effect to not take place. And usually when you're dealing with potentials, you're dealing over a 1 over r instead of a 1 over r squared.
Yeah, and you also got the fact that the force is the derivative with respect to the positional parameter of the r. Of the u, I mean.
So if you would calculate using this metric how the radial motion is, you would take the radial geodesic equation. We would have to solve something like this, right? Oh, and this is an r. Okay, good. Now, gamma, the Christoffel symbol, is not metrics. It's derivatives of metrics, some particular sum of derivatives of metrics. Now, this whole thing, if you really want to compare it to Newton's physics, second derivative with respect to time, so it's acceleration. Sure, it's the wrong time. It's not t, it's tau, but sure, it's an acceleration. And this then takes the role of a force. Acceleration, up to a factor of the mass, should give you the force. If you really want this to look like Newtonian physics, at least in some range, then you want this whole thing to become 1 over r squared.
Yeah. So the antiderivative.
The antiderivative of 1 over r squared, that is the one you should, that should be your metric tensor elements. That sort of makes sense, right?
Yeah.
So Rodrigo used a very nice way of putting it. He used the word potential. Yeah, he also used the word potential energy, I think.
Yeah.
Now potentials, forget about the energy part, potentials in physics mean a thing of which you have to take derivative before you end up with a force.
Yeah, basically.
Well, that's really what we have here. Also electrodynamics people, same thing there. You get your electric and magnetic fields, which up to a factor of a charge is your force, by taking the derivative of your vector and scalar potential. A potential by definition is a thing of which you have to take derivative in order to get a force. So if you want, this is more like a potential than it is a force itself. Excuse me, sorry. This whole thing is a force, but that means since this thing consists of derivatives, the thing of which you take derivative is very much like a potential. Now, of what are you taking derivatives? Of your metric tensor. That's what your Christoffel symbol is. So that gives you maybe a new feel for what a metric tensor is. It's this big block of 16 potentials. I'm not saying explicitly not saying potential energy, just potentials. And how do you get forces out? By taking their derivatives in this particular combination. Now, that means if indeed if you want to get the 1 over r squared out because you want it to look like Newtonian gravity, then apparently this has to be some sort of anti-derivative of 1 over r squared that gives you 1 over r. So if you were to get something, some deviation from Minkowski space-time that looks like Newtonian gravity as you get closer and closer and closer, you expect a 1 over r, not a 1 over r squared or 1 over the tangent of r, or the logarithm of r, or something like that. So it would be a very good guess. Okay, so we have the 1 over r's down. Why no 1 over r's here, by the way, this part?
Because does it have to do with time and length, I guess?
I mean, your distance from the object that you're analyzing stays the same if you go around in theta. Same, that's fine.
That sounds like a symmetry argument.
Symmetry.
Yes. Do you remember last week, if it's correct, do you remember last week when we derived the metric tensor for, forget about Minkowski, just Euclidean space in spherical coordinates? We found this 1 times dr squared, something something, forget about the time part, it's just space for this moment. Now, this Minkowski, this Euclidean space was completely spherically symmetric. And we saw that this was the answer. So if you're going to look for some description of spherically symmetric gravity, then again, you expect something like this because of the connection to Newtonian physics, and you expect this because of the spherical symmetry. Okay, so that's perfect. Okay, should we have any thetas and phis maybe in this extra part? We argued that it should at the very least be something over r. Why not thetas and phis? I mean, 1 over r part we understand. Well, why not thetas, why not phis?
I mean, I would say the same symmetry applies
Yeah.
here as well.
Yeah, of course.
Exactly.
That's always yes. You expect that whatever effect you will find, it should not depend on phi and theta. Well, it sort of seems to limit our options, right? You can quite well guess your way towards the right expression. Not fully though. Let's make things a little bit more complicated. This k, we understand 1 over r. Let's look at the numerator now. Exercise 1a is explain on physical grounds why you expect it to be something with a mass. K is something with a mass.
Because gravity depends on mass.
Okay.
So that means that the effects will depend on mass.
Okay, so that means that you would expect, because yes, in order to make the deviation from Minkowski space-time, right, this is deviation from Minkowski, you would expect that it is some function of mass. We can do a little bit better. It's a function of mass such that if the mass is 0, the k is 0. Okay? But I mean, I can think of many functions k of m that are all 0 for m is 0. So, man, what should we do?
Well, we know that also the mass is constant, that it doesn't change.
If you go back to Newtonian physics, it's also proportional to mass, so you could make that comparison.
I actually like that. I mean, that is certainly an argument. I would say, remember that we want to get back to Newtonian physics. You have to take derivatives.
Yeah.
Well, we made use of the fact that you have to take derivatives to get the 1 over r squared out. Now, nowhere in the Christoffel symbol are you going to take any derivative with respect to m. So that means the m that you're going to put in your metric is the m that's going to end up in your final expression.
Yeah.
So if you want it to come out as proportional to m, then
Just a minute.
you have to do m. You cannot have any function of m because as you go through the calculation of the Christoffel symbols, nothing will change to that with that m. So it seems like the only option is that there is an m. It's m itself. There's not an argument to make why this is m. And that has to do with units.
Yeah.
So this is a good argument, but maybe we can use the look at the argument as well, just to drive the point home. What should this guy's unit be ultimately?
Unitless.
Kilograms over meters.
Yeah, that's what it is. What should it be?
Unitless.
Yes. Unitless. Otherwise, you cannot subtract it from 1.
Yeah.
Okay. So, well, let's check. Symbol-wise, when I do these square brackets, I mean unit of. So the unit of what we have now is kilogram over meters or something like that. Well, that certainly is not unitless. So we might want to put some g's and c's back in. Those are the only numbers we took out, right? We put them to unity and let's put them back in. Those are the only two that we can play around with. Those are the only ones we can put back. So any suggestion on how to put g's and c's back in such that this thing indeed does become unitless?
Don't remember what the units for G is.
Well, we can derive it right here, right now. I mean, the unit of C is
Yes.
no problem there. Okay, unit of G.
Isn't it kilogram meters per second? Or kilogram meters?
Meters per second. Yeah.
Yeah.
In all honesty, I always forget what the unit is, so I always just rewrite it.
From newtons.
Yeah, just from the fact that I know that G times kilogram squared over meter squared, Newton's universal gravity, should give you a force. So F equals whatever the unit of G is times mass squared over meter squared. So that's kilogram squared meter squared. Unit of force is itself a Newton, which is a kilogram times an acceleration. So this should give you kilogram meter second squared, right? Unit of force is meter per kilogram times acceleration. Yeah, and then it just becomes an algebraic exercise. This should be kilogram. This should drop out. I find it G equal to kilogram meter to the third second squared. Honestly, I always forget what it is. I know it's some combination of
Another kilogram on the denominator.
and I think
Yeah,
you're right.
it is.
Yes, I'm sorry. Kilogram should go down. There we go. But I think this is okay, so we have a kilogram of a meter and we are free to put in G's and C's to make it unitless.
If you put in 1g, the kilogram will cancel, and the meters will become squared, and then you'll have the extra seconds.
Just divide by
And then
C
you
squared.
divide by c squared.
So yes. Obviously this then has to be this. And now the units are fine. Now that wasn't the original question. The question was, why do we take this k function to be proportional to m? The Newton argument, as in it should look like Newtonian gravity, is fine, and it's just showing you a different way. We can make it work by squeezing in g's and c's if it is proportional to mass. What if it just so happened that we had chosen that this one was proportional to mass squared? So I'm going to pretend there was mass squared all along. Then the unit would have been kilogram squared meter, but it still should be unitless though. Question: how to put in g's and c's such that this combination becomes unitless?
Maybe G squared on the dog.
Well, you certainly should do that, because the only way you can get rid of kilogram squared is by g's. C's will not help you. Okay, so let's do that. So the g squared, that gives you m to the 6, the kilogram drops out by construction, and at s to the 4, m to the 5, s to the 4.
Oh, so it's impossible to construct it.
Yes.
Which means m squared.
Yes, if m squared, there's no way that you can put c's in to make it unitless. There's literally no way you can do this. So m squared does not work.
But any m to the odd number would work.
To the odd would work.
Yeah.
Let's try that. M to the 3. That will give you kilogram to the 3 meter. We need at least 3 g's to cancel the kilogram to the 3. So let's do 3 there. That cancels this one. Then I import an m to what power? 9. Oh man. Okay. Divided by second to the 3, that's 6. Then I get meter to the 8, second to the 6. Still doesn't work. That sucks. Now you can continue this exercise as long as you want, but that means every power of m that you would have tried there cannot be made unitless by g's and c's. That also tells you that apparently it's just m. As a final comment on that, you might think, you know what? This k of m that I don't know, we've only checked whether it is some power of m. And we saw that if you assume it's one power of m, then there's only one power that makes it work, maybe to the power 1. But maybe a random function. Just anything that depends on m, it's just not a power of m. Logarithm of m, or whatever. I claim that it's still impossible.
Well, the units wouldn't work either.
Yes, but how to show this? We've shown that m to the power something only works if it's to the power 1. But there's still other functions that are not m to the power something, just general functions of n, and those are also all of them excluded. And I'm looking for an argument why that is the case.
If you did the same unit calculation that we just did, you get something that was impossible to make unitless, right?
Yeah, but how can we do the unit calculation if I haven't specified what k is?
Well, if you pick one and you did it.
Sure, but now you have to have infinitely many functions to pick and check whether you can make the unit.
You're saying there's no like induction you can do to rule out all of them.
How about this?
Yeah.
Well, this is a Taylor series. Any function, well, it has to have some conditions. That is, continuous, differential, the basic conditions. You can write as a Taylor series, yes, in n. Now, which one of these many terms in the Taylor series you can make unitless? Only the first one. So even if you try to get all functions that can at least be written as a Taylor series, then still the conclusion is the same.
True.
So that's another way of saying that apparently it really should be an m. So we have two good arguments here: Newtonian physics and unit physics.
Where does the 2 come from in the actual
Schwarzschild
tensor?
That's a good question. Because there is in real life, so there's a full solution by the way, it's just in real life there's an additional 2. Yeah, where does it come from? The answer is really nowhere, because it's unitless, so we cannot use one of our previous arguments, right, to get the 2 in there. You also don't get it from the, if you actually take the equation that gives you the metric tensor, the Anderson field equation, it will also not give you that 2. What is the argumentation that we saw before? It has to look like Newtonian physics. We just know there's a constant times mass in there.
Yeah.
You want it to look like Newtonian physics. You go through your geodesic calculation, blah blah blah. You will end up that it should have been a 2.
Okay.
So it's just by making sure that it connects seamlessly to Newtonian physics. If you go far away from the black hole, then it says it should have been 2 all along. So yeah, we can guess our way towards the right expression, right? Quite far, actually. Now, before we actually go and start calculating stuff with this, let me make one final comment. This one, you cannot get from your comparison to Newtonian physics. Maybe you can give me an argument why.
Because it's time.
Yes.
You don't have that in the
Sorry,
Newtonian equations.
Which one?
This one. There's no time dilation in the Newtonian
Yeah.
physics, so we have no idea what should be in front of there. There's nothing to compare it to. So,
Then how do we know that there's a 2 in front of that as well?
oh, this then does come from the Einstein field equation.
Oh, okay.
Yes. So the fact
So
that
that's a nice coincidence.
the fact that this one, well, what is coincidence? I mean, it obeys the equation, but the fact that this term is a 1 over r, we've argued that because it should look like this for Newtonian physics, right? The fact that there's an n up front, we get 2 different arguments for. The fact that this guy comes with the 2 is because you make it look like Newtonian physics, to make it seamlessly go into Newtonian physics. If gravity becomes weak or you're far away from the black hole, but it only gives you this part, and this part you cannot get from comparison to Newtonian physics. Now, ultimately, your metric tensor will have to obey the Einstein field equation. So if you would take your guess of this thing, put it into an Einstein field equation, and just ask what this should be, then it gives you this expression. So at some point, we will need the Einstein field equation to fill in the last remaining gaps.
Oh, so that's how it was calculated?
Sorry?
So that's how it was calculated?
I don't know, to be honest. I think that's I've never read the original Schwarzschild article, but I think that in his original article he never specified the mass part. I could be wrong about this. He just says there's a constant here. But I don't know if he actually made the step to say that it was mass. So my PhD supervisor, who was also the person that I did general relativity with when I was still a student, was very pedantic in these things. He also knew about the Droste thing, right? So he called it the Schwarzschild solution, because Schwarzschild was the first person who had it published. But Schwarzschild had it written in different coordinates. It was the same physics, but different coordinates.
Which coordinates?
Yeah, I guess the Schwarzschild coordinates. But nobody uses them, so I wouldn't know what they look like. But you know, different coordinate systems. Again, same physics.
Seems
right?
like it would be obvious to do it in spherical, though.
No, that is probably true. But then again, maybe it isn't.
Yeah.
No, we'll do an exercise in a moment where we have to think twice exactly what the R means, for instance, in this context.
Okay.
Anyway, we'll see in a moment. So my PhD supervisor, when he taught the course in general relativity, he always called this the Schwarzschild solution in Droste coordinates, because Droste actually did use these coordinates.
So we get some recognition.
Yeah, he got some,
Good for
but
him.
only by choice of coordinates. It's sort of like a consolidation prize. My PhD supervisor was extremely pedantic in that. He never said Schwarzschild solution. He also said Schwarzschild solution, but he also said Droste coordinates. Okay, so now I think we have some understanding of what this thing means. Yeah. So let's do some exercise. By the way, we now went through exercises A and B. Remember that during the main lecture we discussed what dt meant and what d tau meant?
Yeah.
And that you had to be careful because dt, I mean, there's many people who can measure time, and whose time was that? And we found that it was the time as measured by a person at infinity who himself does not move with respect to the black hole. That is what we saw.
The bookkeeper.
The bookkeeper, yes. Because you can at least always relate your numbers to that guy. Let's do the same for R. There's a dr in there as well. There's an R in there. Whose R is that? Who measures those amount of meters? Yes, it's a radial distance from the center of the black hole. But just as time ticks differently depending on whether you're close or far away from the black hole, that's the time relation that we derived during the main lecture. It might also be that the amount of meters gets stretched.
Yeah.
squeezed, or when you get closer to a black hole. So it's certainly not obvious if you say dr is 2 meters. Who is the person who measures at 2 meters? Is it somebody who's far away? Is it somebody who's in the black hole? Is it somebody who's at the center of the black hole? Is it somebody moving about the black hole?
I think it's the person who's far away.
Can you
Shouldn't it be the same person who measures the dt and each other coordinate?
Why?
Because then otherwise you don't have a consistent set of coordinates.
Absolutely you do. I could, you know what?
Okay, you're still in spherical coordinates, fine, but
it would be a very crappy coordinate system that you take one guy's time and the other guy's.
yeah.
You take 2 different bookkeepers, right? Right, one for space, one for time.
Yeah.
It's not inconsistent. It's just impractical.
Maybe we can try to find it in the same way we found for time, like by doing the line element again. Okay.
I'm happy to describe, but somebody needs to point me in the right direction. So the question is, how can we find out who is measuring the dr? And there is a sneaky suspicion that it's the same bookkeeping guy as who does the time measuring.
I feel like you'd have to justify anyone other than the bookkeeper. Like it makes sense that it
Yeah, but if I'm extremely evil, I'm just going to throw a metric tensor your way that I explicitly made with 2 bookkeepers, yes? One for space, one for time, and one for theta. And
So it is possible. It is possible to do it with different
Yeah, sure.
observers. We
Yeah.
just don't because of convention.
Uh,
Or is there a mathematical
There's
reason
no
why?
mathematical reason. If I were to take the guy at infinity and I'm going to define a new guy who is a particular distance close to the black hole than the other guy, so this guy's r is replaced with the other guy's r
Yeah.
plus a constant, well, that actually won't work because the constant will drop out in the d, the
Yeah.
differentials. Okay, let's take another guy who's moving radially.
Mhm.
Then one guy's dr is certainly not the other guy's dr. If I'm extremely
Yeah.
evil, I could do the following. I could say, hey, let's take r, bookkeeping r,
Mhm.
the guy at infinity. Yes, it is the guy at infinity, by the way. Okay, but we have to prove it. So let's take the guy at infinity. Let's take this guy's r, infinity r, replace it by some new guy's r, plus this. Then this dr would now turn into vr dt squared would give me this, and I would have had vr squared dt squared.
1 plus v.
And that's the one measured by the person going at a velocity.
Oh yes, I'm sorry. Ali is right, by the way. I'm sorry. This is dr
1
plus
dr.
vr dt. Then square this. I would get your dr squared plus vr dt squared, which would end up here, plus now a dr dt that appears twice.
Cross term.
My metric would, my line element would look much more difficult.
But it would still be valid.
It would completely be valid.
But
It's
then the
just-
answer to the question whose dr do we use is anyone's.
No. In this particular case, it's a very specific one. The only thing that I'm showing you now is that taking this dr and changing it to some other bookkeeper, one that happens to be moving radially through the space-time, is perfectly allowed. You just end up with a much more difficult line element. And it will not be doing you any favors. Question still stands. Is this the same bookkeeper who does the measuring of time? The answer is yes, but can we prove this? And no.
Well, you've shown that if it's not, then you get a VT instead of the DR.
I just showed you in one particular case that is true, yes.
In any case, they will be moving with respect to each other.
Okay, that I assumed by what I showed you before that this DR was, or that I already knew that it was the bookkeeper guy at infinity.
Okay.
Okay, so please use your intuition. Could be sixth sense. Could be physics intuition. Could be male or female intuition. I'm happy with anything. Just give me an argument why this DR is indeed also
Just
valid.
makes
If
more
the
sense.
DT and the DR will be from a different observer, they'll always be moving with respect to each other in the case that we just discussed. So there will always be some Galilean transformation in one of those DT or DR. Maybe there's not a VT in DR, maybe there's something instead of DT.
But who says that this dr was not a moving dr to begin with?
Yes, but if you have one that is standing still at infinity.
That is indeed yes.
Okay, I don't know.
Do you remember how to calculate distances?
Mm-hmm.
Just in general. Just I give you a metric of a space. Forget about the time now, just a space. Do you remember how to calculate a distance?
We write the line element of the distance.
Integral of theta
Well, is an integral d tau though?
between whichever 2 points you want the distance.
Well, that is true. You know what? I'm going to go with this suggestion. I get the C's and the G's out of the way. Okay. Oh. You know?
Take out dt squared. Well, take out dt.
Well, we certainly could, but remember, we're looking for a distance.
Then dr.
We might want to take a dr. Let's do that.
Data must always that integral must always be minimized.
If you want to calculate how this thing moves through space-time, the answer is yes. But we're not. This is not our question. The question is not how does something move through space-time. Our question is a different one now. Now the question just is, what is the distance between 2 points in space? Forget about time. Just space.
Well, now you're differentiating the coordinates with respect to the other ones. So if you were using different observers, then there wouldn't be any direct dependence between, say, the theta of one guy and the r of the other guy.
So what does that mean here?
That just means that those derivatives wouldn't make sense.
Is in they're all zero or?
Yeah.
Yeah.
And then you have a negative number there, I think, right?
Yeah, but if that were the case, this is all zero. This is zero. There's no derivative here. This is zero. That's zero. You get square root of a negative number. And something obviously goes wrong here. Hey, if you measure a distance, think about your special relativity. If you measure a distance between 2 points, you want to meet between two events at the same time. Because otherwise, whatever you're measuring, it's not a distance. This is something, a lesson that you might have picked up from special relativity. Measuring distances, by definition, means doing it at the same time.
So that tau is 0 should be
Is tau zero, really?
at the same time.
But it's not the time between you. You're just saying that you're putting the two locations. You're measuring the two locations at the same time.
Okay.
It's not the time between events or anything.
Okay, but that will mean here that this thing is zero.
No, but he's right. That's what you used to do in relativity. We used to say that the event of measuring the first, and then the duration between.
Yeah,
the
if you
measurements.
set them as two different events, then tau should be 0.
That tau should be zero.
Yeah.
But I mean, tau is not zero. I mean, we have this line element, and it certainly does not give you tau is zero. Let me write down a suggestion, and let me chew on this for a bit. I'll just continue writing for just a bit.
we going to find like a situation in which delta t, delta theta, and delta phi is 0?
Well, that depends on context.
Like, you know, like if you found an observer maybe that has the rating 0, you could relate the S with the R somehow and find that it's the same, or something like that.
I'm not sure I follow.
Like if you have an observer, like how we found like the time dilation is like you said that an observer is like very far away, and we found the delta tau is delta t.
Yeah.
Maybe we could take the same observer and found like a distance he measures. We found that that distance t is equal to dr, so we get the s equal to dr somehow. Something like that.
Well, let's first get rid of this thing. By definition of measuring a length.
Yeah. dt 0. Not theta.
Yes.
True.
You see this?
Mm-hmm.
Okay. Now, the exercise is a little bit more specific. This exercise D, to show that dr is the radial distance measured between two events as seen by an observer who is stationary and infinitely far away. It's the radial distance that we're looking for.
So the theta and the phi are 0.
Not generally, but in this particular exercise, these are
Since
0.
the observer is very far away, then we get the s is equal to
Yes, if the infinite, so we've now taken this. First of all, the fact that this is 0 means you measure at the same time, so you're really measuring a length. That requires dt to be 0. The exercise says, take the observer who measures the things at the same location, at the same, what's the word here? While he himself is not moving. This gives you that these two are 0. Yeah, and then finally, you have this thing here.
but r is very big because we're infinitely far away,
Yes.
so it remains as equal to dr.
Yes. That's what the exercise says, yes? Look for that one observer who's looking at things from infinitely far away. And himself is not moving. Himself not moving means this is 0, this is 0. Infinitely far away means, where's the thing? Is that this one goes to 0, and the fact that he's measuring a length means that dt is 0. Because otherwise you're measuring something, but you're not measuring a length. And that really solves the exercise. It tells you that the r apparently that you find in your metric tensor, your line element, is apparently the r, again, as seen by the guy infinitely far away. That's what you now find. So it's really the same bookkeeper. Again, it did not have to be.
Yeah, but that just showed that it's context dependent then. Because you could have picked a different exercise in which d theta, d phi weren't necessarily constant 0 and
No, but I'm fixing which of all the observers that I could have had. I'm fixing the one that is not moving in angular direction. So if your statement is that you could also have had observers for which these had not been 0, that's true. They would have measured different lengths.
But you just showed that it's valid to take the bookkeeper as the observer.
Yes.
You did not prove that you can rule out every other observer who's not the bookkeeper.
No, but I didn't say that you can rule out the other people. Other people will also measure lengths. Other people's lengths would still be this full expression, but well, without the dt part. So every person would measure a length by this square root.
Mm-hmm.
And how much they would actually get out, how much meters they would get out, that's the ds. Well, that depends on how they themselves were moving, how their d phi and d theta.
But the t is always going to be 0 because everyone will try to measure length at the same exact time, right?
Yes.
Like the beginning and the end point of the length.
Yes.
I think I misunderstood what is asked when you say whose dr and d phi and d theta do we use.
Well, okay.
What was what are we actually trying to prove with this?
What I wanted to, with the exercise, asks of us is show that dr is the radial distance measured between two events as seen by an observer who is stationary infinitely far away.
Okay.
So show that the dr as it appears in the line element is equal to the amount of meters that somebody would measure if he had been infinitely far away.
So that dr and r are from the bookkeeper,
Yes.
as the bookkeeper sees it.
So it's the same thing that we did with the dt.
Yes.
And if you did it with the other coordinates as well, you would. What if you wanted to show that d phi is the d phi for the bookkeeper?
There it actually doesn't matter, because if you go through that exercise, whose d phi are you actually measuring? Which observer is that? You will find that all observers agree on the d phi. There's no difference between an observer very close to the black hole and what he measures for d phi and what the other guy measures for d phi.
Okay. What if one of the observers is orbiting?
Then life changes, because then all of a sudden your thetas and your phis have become time dependent, and their d phis and d thetas will not be zero.
Yes.
So your question now is suppose that it wasn't, that we did not single out this one observer at infinity and far away. How would they measure distances? That's a good question. And the answer is it's always by this equation. You just have to put in the right functions for theta and for phi for the observer that you're looking at. Now the exercise specifically says take the observer infinitely far away, etc., the bookkeeper observer, and then show that what he measures is actually the dr that was in the expression all along. So that teaches us something. It tells us that this r that we had here and here and here and there is the amount of meters as measured by the guy infinitely far away. So he's sort of like a double bookkeeper. He keeps track of times, and he keeps track of distances, of radial distances.
This kind of conflicts with the intuition we tried to build of there is no special reference frame in special relativity.
Oh, but there isn't. Well.
I know it doesn't actually contradict it, but it seems like it does in some sense.
What we now have is we have picked our reference frame, namely the Schwarzschild black hole reference frame. Now, I think what you mean is of all the people whose coordinates you could have put in your line element, why did we take this particular guy's coordinates?
Yeah.
Well, you have to take somebody's coordinates, yes? I mean,
Yeah.
somebody has to measure space, time, space in three directions, and time. There's absolutely nothing special about this coordinate, about this particular person, in the sense of physics. The only thing special about this particular person is that it happens to be his coordinates in which the metric tensor was written.
Okay. The metric tensor was written using those coordinates.
Yes, but there's nothing special about that particular person over the other persons.
Okay, so Schwarzschild himself and the other Dutch guy
Yes.
chose that beforehand and then derived that
Yes,
metric
and then
tensor.
derived that it was, apparently this particular observer has to be that observer. So let me give a sort of example, metaphorical example, but suppose that you would say, you know what, let's take my length from feet to the crown of my head, which is 183 in meters. Let's call that a new unit. Okay, let's call that the Google. So I by definition, I have a length of exactly 1 Google. Now, you take one of you people, well, let's take a very tall person, right? Now he's going to be, I have no idea, 1.1 cuckoos.
1.05 cuckoos.
1.05? Okay. You're not that much taller. Okay, fine. So if we would write down what each of your lengths is, or heights is, in terms of this new unit, numbers would come out, yes? And then you would ask, but what is so special about me that my height was the unit with which you compare everything else? There's nothing special about me. I'm not any more different in height than you guys are. Well, I'm different in number, but there's nothing special about me having, there's no objective reason why you've chosen me as the unit for your lengths, for your heights. But if we are going to define some unit, we have to take somebody's or something's length or height as the base unit, yes?
Yeah.
There's absolutely no reason why we took the cuckoo as the measure of things and not the yogi. We could have also written everything down in yogis. Numbers would have changed throughout. It would seem as if this guy is now more important than I was before, or compared to the rest of you. Nothing has changed. It's just you need to have some base unit in which you express things. Now, somebody could come in and would say, well, I hear people are measured here in yogis. I wonder which of these 8, 9 people is actually the person who agrees with one yogi. Measure. Oh, there he is. That's the guy. That's the one yogi guy. What's so special about him? Nothing. No, really? Well, there is. There is. But it might give that person who came in the impression that there's apparently something special about everybody being measured in his height, in his unit. There isn't.
So the bookkeeper coordinates is like the unit of the
Yes.
metric tensor that we're using.
Yes.
And if we chosen another observer, say one who is rotating or something,
Yes.
we would construct a different metric tensor that
Yes.
still described as spherical mass.
Exactly. It would. That's
It
exactly.
would just
my
look
point.
different.
Okay.
Okay.
The space-time looked exactly the same, but because you change your unit system, you measure everything against not what we now call a bookkeeper device, but somebody else. Numbers would come out completely different.
Yeah.
The function would probably come out very different too. It would still be the same space-time. And then you would have come along and said, what is so special about that bookkeeper? Why did we take the one at infinity? Well, you have to make a choice somewhere.
Okay, I see.
And just like there, in your figurative example, there might be someone different from him, but the same height.
Yes.
Could there be an observer also like moving or a different location, but
Yeah, that is
just somehow
that's
coincidentally the same numbers and form?
That's a good question. Is there a second observer around who happens in his coordinates end up with exactly the same
Yes.
expression?
I mean, always specified was at infinity and not moving, so it can be the
It could
entire-
be any person along that circle. So yeah, you're not uniqueness in that sense. Yes, that is true. Yes.
And in Minkowski space-time, it doesn't matter.
It
They're all
doesn't,
the
really
same.
doesn't matter.
Okay.
Because every person, as long as he stays within the same Minkowski
Yeah.
metric and it doesn't go to xt, x prime, t
Prime,
prime,
yeah.
y prime, everybody will be the same.
Yeah. Okay.
So what we now have is a ring of bookkeepers who all agree, whose units are all the same. And in Minkowski space, it would have been every single person everywhere ever.
Okay.
Yes. Okay, now, one final step and then let's go for a break, but in order for this to hold, I did make the explicit change from ds squared to minus d tau squared. Yeah. Do you have any trouble with that? I mean, I just randomly inserted the minus sign and defined a new thing and
Yeah,
went
why
with
did-
that.
Why is it minus?
Isn't that how it's defined? ds is equal to minus cdt.
Well, yes, that's a definition, I agree. But you can explicitly see now that because measuring lengths is by definition doing this at the same time, this now by definition will drop out. So obviously this must be length. So the minus sign is defined in such a way to make sure that whatever you have end up on your square root sign will now be a plus number.
Okay.
So it's not just mathematical necessity. If you follow this logic, you actually find your ds is dr for this particular observer, and for observers, so you find something else. So this is not different, by the way, than what you already knew from your special relativity. There we have d tau squared is minus plus dt squared minus dx squared. And you can ask, what does d tau mean? Well, we discussed, well, it means by definition the amount of time that passes for a person who sees two events happen at the same location. Yes? Because by that definition, that means dx is 0, and you would get, oh look, that's what d tau means. But I could also say, you know what? Let's take two events that happen at the same time, a length measurement. Then obviously the amount of distance you will measure should be dx. Agreed? But then you would end up with this expression, which doesn't make mathematical sense.
Is that equivalent to using the covariant x mu instead of a contravariant x mu?
Because the swapping minus sign, you would
Yeah.
say something like that. No, not really, because I don't think so. I have to think about it. I don't think so, but
Okay.
I have to think about it. The only point that I want to make here is that d tau has many different meanings. It's an amount of time, it's also an amount of distance. Which one you mean depends on context. If you restrict yourself to a situation where this particular observer sees two things happen at the same location, then d tau means the amount of time. If then again, you're going to take d tau and you're going to restrict yourself to a situation where somebody measures things at the same time, then d tau all of a sudden means minus dx squared. So what do people do? They say, you know what, we're going to define d tau squared is minus ds squared, so get rid of these minus signs, and now we understand that ds really is the amount of distance. That's the only thing that I did here. I just copy pasted this from Spatial Relativity. That is that if I want to have a distance, I'm going to interpret my d tau as a distance, then I have to have some extra minus sign in there, and take my dt to be 0. And then end up here. So that brings us to a very natural moment for a break. And let's do some spaghettification after the break.
Or is it the one where you're like,
Yes.
Really?
Yes.
Spaghettification.
Spaghettification.
Can you show us in the end how you reach the singularity? How you reach the infinity number?
Yes, there is actually an exercise. The third exercise is, excuse me, the fourth one, where the question is, suppose that you are radially moving towards the black hole. You tell me what happens.
Well, yeah. Is it the time and space swap?
The answer is yes, but I'm very surprised that
Wait,
comes up here.
what?
Okay. Yeah. Never mind. Because
It's in waters, but it is related to this discussion actually.
okay.
I
I
cannot help you.
don't know how that comes up because it's the first time I'm seeing all this, but
Well, people don't want to hear this, feel free not to hear this, but I cannot help myself. As in, if you want to have a break and not be bothered with physics in your break, fine, but I'm going to answer. If you take your r to be smaller than 2m, you make r smaller than 2m here. If r is smaller than 2m, then that means this number is bigger than 1, and that means 1 minus 1 becomes itself negative. That means that this thing in front of dt overall now carries a minus sign.
so it's like as if the dt is now dr.
Yes, that's the swapping of space and time that happens when you enter a black hole.
how is that like possible? Like, how would that feel like?
How would it feel like?
Your age become how long you are, and how long you are at your age.
It feels like you cannot escape from the singularity because the singularity is now in the future and all that
No, guys. I mean,
stuff.
it's not
Yeah.
that all of a sudden you're 183 of length. Your one cubic all of a sudden becomes your age or something. like that, right?
183 years.
No, but you do see mathematically that this happens, that if you make r smaller than 2m, then the overall number in front of d tau dt becomes negative. And here the same thing, the swapping of sign also happens, this now becomes positive. But using this argument that we were having here, that means that all of a sudden your d tau has become a distance and not an amount of time anymore. And the other way around.
So I have a quick
Crazy.
question. But
Sure.
this isn't actually specified just for a black hole though. So it's saying that if r is always less than 2m for anything, then
Yes.
that seems confusing though. Like
No,
if you take like the Earth for example.
Yes, but let's do a quick calculation, because this 2m is the moment where things start getting weird, okay?
Yeah.
In fact, if you are at 2m, notice that this thing becomes 0, so your time dilation becomes some 0-ish. Somebody's time will be 0, even though the other guy's time keeps on running. Your time comes, if you do the calculation fully, you'll find that your time comes to a standstill at the moment that you go through a black hole. Okay, so So weird things happen at 2m. One of them is the swapping of space and time. Or I should be more careful in my phrasing. The role that they play in the line element, that swaps.
Yeah.
Now, why don't you see this happen when you every time that you take 2 fighters down there and then you're well, let's just put in some numbers. The mass of the Earth is 6 times 10 to the power 24 kilograms. Sure, let's make it 12 because of the 2. Newton's constant is 10 to the power minus 11. Yes, there's a 6.7 in front. I don't care about those. It's the order of magnitude that I care about. And C squared is 10 to the 16, and the 3 in front squared gives you a 9, so it's about 10 to the 17. So I get 10 to the 24 minus 11, 10 to the 13, 10 to the minus 7 gives you about 10 to the power minus 4, which is in meters, so it's about a millimeter. No, it's smaller still. Actually, it's a 0.1 millimeter. So where's this point at the Earth? Measured from the center of the Earth, where you see the strange thing happen. That's 0.1 millimeter away from the center of the Earth.
So what happens to you if you theoretically manage to dig a tunnel that deep?
Well, you won't be allowed to use this map to use this space-time line element, because this only holds in vacuum. So at the moment that you get to the surface of the Earth and you go dig into the Earth, then this thing doesn't hold to begin with. This only holds for when the right-hand side of the
yeah, because then it's not a spherical mass around you.
So then even the Earth has like a Schrödinger radius.
Yes.
Like a very, very tiny.
Yes, but it's ridiculously small and it's way, way, way deep within.
So you'll never like reach it.
No, but even if you would dig that tunnel, you would still not get there, because within the crust of the Earth, your Schwarzschild space-time doesn't hold. It's not in spherical space-time anymore.
So there's no way to actually go to the Schrödinger radius.
It does
No,
mean that
but
if
you
you want to see this effect, you have to take all the mass of the Earth, squeeze it together in a radius smaller than 0.1 millimeters. This is when
fire.
you would start seeing those effects.
Dublin, that's also really good. Yeah.
I love history.
Okay, people,
Yeah,
let's
history
do
is also beautiful.
a fun exercise that has to do with spaghettification. I'm sure we have dinner time right now anyway, so this might be a good moment to talk about food.
Past dinner time.
Spaghettification. We are going to answer the following question. Here's our black hole. Here's that very special distance 2m. Let's try to think about the following thing. Here's an observer, let's call person B, and at infinity there's a bookkeeper person, he's at position A. I was trying to draw this radially, but I messed up. There we go. And this guy is at infinity, stationary, blah blah blah. Okay. Now, I'm curious about the following. Suppose that there is an amount of radial distance. You can make it as complicated as you want by taking non-radial distances. For the sake of argument, I'm going to take a radial distance from this point to that point as seen by this guy. You would ask him, how many meters is it from where you are to where this point is? Next thing you're going to ask is the bookkeeper at infinity. You're also going to ask, how many meters is it from here to here? You will not get the same number. You will get some sort of, well, Lorentz contraction, but it just so happens that it works the opposite way. You get Lorentz dilation or something like that. Now, in special relativity, changes in length have to do with these people moving with respect to each other. No movement here. All of
They're both
is
stationary.
They're both stationary.
Okay.
So the only effect that could happen can only have to do with the fact that there are different positions in your metric. It's because of their R that they are different. I want to relate how much this guy says that this distance is versus how much this guy says that this distance is. I want to have some sort of time dilation formula, but now for radial distances.
Okay.
Suggestions how to calculate this. I wrote down 2 equations for you. This is the one you have to integrate if you want to know the amount of time. This one you have to integrate, it's just the same with a minus sign, if you want to know the amount of distance.
So we do the second one.
We do the second one. And who of the two observers do we start with?
Let's start with
A.
which is like the
Yeah.
Okay, well that is easy, right?
We've already done it.
We have already done it. The amount of distance from here to here, let's call this one R1 as measured from the center of the black hole. Let's call this one R2. Just okay. Then the amount of distance between these 2 points is called the delta R. Well, it's just what is it? R1 minus R2. Am I correct?
R2, oh wait, no.
Well, whatever gives you the positive number. Okay, so that's it's R1 minus R2. Great. No surprise here. Before the break, we had already seen that of all the people whose units we are using, it happens to be the person at infinity. So obviously, this guy at infinity will measure this distance as literally just the distance between these two numbers. Alright, now that's easy enough. Let's take the B guy.
So what's the 2m?
That is the radius. That is the radius where the black hole ends. So it's the radius where these two things start having strange properties. And people call this the size of the black hole.
Is that the Schwarzschild radius?
Yes, that's Schwarzschild radius. Or event horizon, it's just all different names for the same thing. It's at 2m. There's also a 3m radius here. It's a photosphere. You have a 6m radius, that's the ISCO. All kinds of interesting stuff happening there. But not important for our conversation right now. 2m, famous number in Schwarzschild physics. Okay, so I want to know how much this guy thinks that there are meters between R1 and R2.
Oh, we do the integration of ds.
Okay, Tom.
And so ds is equal to the square root of all of that. However, because he's measuring distances, dt term goes to 0.
Okay.
Same for d theta and d phi, because there's no changes along those. The only difference is that for him, for that person, the r is not at infinity, so the term won't drop. It's just going to be a difference of r2 minus r1.
Agreed.
Yeah.
I mean, I'm just describing what you were saying. I think
Yes.
this is it. Oh, we are integrating. The metric is written in terms of this guy's r. So we're integrating over what this guy says that this point and that point is. So we have to integrate from is it r1 to r2? Well,
R2 at the
depends.
bottom.
It depends if you measure from here to there or from there to there.
Kind of the same.
So you know what? Let's
R2 at the bottom would give you a positive number.
yeah, let's do that. Let's do that. I mean, we're measuring lengths, right? We're looking for a positive number. All right. Now we have a integration to do here. Forget about physics. We have a mathematical exercise here. Anyone who happens to know what the antiderivative of this crappy thing is?
Wish I did.
No idea. It's some complicated expression. I sort of half know it by heart. Not because I use it all the time, but because of teaching this course every now and then. It's some logarithm of square root or something like that. I mean, it's crap. It's a crappy expression. But in principle, you can do this exercise. So feel free to type it in your Mathematica or your MATLAB or whatever you want to do as an online integrator. I decided when I was doing this exercise, you know what? Just for the sake of having definitive answers, let's take R1 and R2 to be somewhat far away from the black hole. Not as far away as this, but far away-ish. And the reason that I want to do that is because the integration happens to be a little bit more easy. So you can also do it extremely close to the black hole, feel free to do it, but then you would have to do the full integration, which exists, it's just a crappy expression. So for the sake of argument, I am going to approximate this thing by, let's do it in 2 steps. R2, R1. This will give you 1 minus plus 2m over r. See if you agree. It's a famous Taylor series that I plugged in there. Sure, you've seen it in some context before. That's one that I'm using. because in our exercise we are now deciding to have this somewhat far away from the black hole. That means that whatever R, both of these, are a lot bigger than 2m is. And that means that this 2m of R becomes a small number, and then this approximation holds. Right, and there's a -1, that becomes this n, gives you a -1 in front, that makes this a plus. That's easy enough. Can we do this integral?
Sorry.
Oh, no, this is your square root.
Yes.
Alright. Can we do this integral? It looks sort of benign, right? It's only a square root 2. No, there is square root 2 and more. Just say approximation. Right, I mean, this thing is still smaller than 1, so that's our x in our approximation formula. The n is now 1/2, so the 1/2 cancels to 2. So, by the way, this is an excellent approximation, by the way. It looks as if when you've thrown away with loads of information, we're not. This is a good approximation. Now, this integral, I'm sure we can manage. Yeah, all laughing people. Can you tell me what the answer is?
R minus divided by R squared.
R minus
No.
m over r squared.
Yes.
No,
It's a
we're
logarithm.
differentiating now. We have to
Oh,
integrate.
yeah.
Yeah, yeah.
L and R.
It's a logarithm.
Oh, and then we have to put in R2 and R1 still, right?
Yep.
Hey, look. This part gives you the amount of distance that the guy at infinity also measured.
Yep.
Plus n times the logarithm of R1 over R2. You get extra length. That's interesting. So if you have this distance here, in fact, let's take this guy here, and he has a piece of rope with a bowling ball, and he just dangles it towards the black hole. Okay. If it has this guy, so how many meters is this dangling rope? This guy will say, well, look, your rope is 1 meter long. And this is, no, it's not 1 meter. It's your 1 meter plus extra. That's a stretching. Now, it's sort of a benign stretching. Because, hey, look, it's only a logarithm. How bad can a logarithm be? Now, note that we made an approximation that we're not too close to the black hole. Okay.
I don't see from this equation, if you would go infinitely far away from the black hole, that it would approximate R1 minus R2 again. That's not in this equation, right?
Yes, it is. Because if R1, R2 are infinitely far away, then this becomes the logarithm of 1, which is 0.
True.
So that's pretty nice. And you can also take the other, just making this point here, that if you ask this guy how long the little piece of rope is with the bowling ball, he would say 1 meter, and he says, no, it's 1 meter plus extra. So they actually have different opinions of how many meters the thing is. Now, that's quite interesting, isn't it? So apparently, depending on where you are in your spatial space-time, the closer you are, at least radially in our exercise, the more meters you're going to need. Oh, pretty cool.
So, ds measured by b is just a plus a little something.
Yes. This is your spaghettification.
So where does the matter come from that makes it longer?
No, there's no piece of matter being attached to it to make it. It's the space on which it is, the thing exists is being stretched out. It's literally like taking, this is the typical way that people describe space-times, right? That they take a piece of elastic cloth. They draw a little stripe on there and then they stretch it out. You don't need extra ink. Okay. So it's pretty cool. And now we made the approximation that we're not too far from the black hole, that we're not ridiculously close to the black hole. If you want to be ridiculously close to the black hole, you have to do this horrible integral. And again, the antiderivative exists, so you can write down what it is. But you know, we can sort of play around with this, because if you're going to get extremely close to the black hole, then well, it's going to suck. Because if this part, the dangling bob, gets very close to the black hole, yeah, this goes to zero-ish, closer and closer and closer. You take a logarithm of something that goes to infinity, which itself will go to infinity. Right? You make R2 close to the black hole. That means you're going to take the logarithm of 1 over 0-ish. Gives you the logarithm of infinity. The logarithm of infinity is itself infinity. It's a mild infinity because logarithms don't grow too rapidly, but it will give you infinity. Now, I'm smuggling a little bit because this doesn't hold for R2 goes to 0. Right? We made the approximation that it did. But if you do the full calculation, it would still hold the conclusion. So this is spaghettification, and you can ask then, is that a real effect? Or is it just, you know, the kind of what you also have in spatial relativity, the paradoxy kind of effect? If you would compare things and ultimately both of them are right or something like that. No, both of them are not right. In this case, if you would actually be there, and you would take my length again, that would be this. If my length was this here, then here it would have been this plus extra. I would actually stretch out. And yes, there is a physical effect. I would literally feel my body being stretched away.
So you would feel it, or it would happen?
No, it would both. It would happen and you would feel it.
Because the actual pulling is happening due to
the actual
gravitational
pulling is happening.
Oh wow.
Now that is very different from spatial relativity, where, you know, depending on who you were, what corner frame, things looked smaller or bigger, or these things. That was just having to do with you having gone to a different coordinate system. This is an actual effect, and that has to do with the fact that, again, curvature depends in general relativity on positions in space. My head is at a different position in space than my feet are, so both will feel a different amount of curvature. I will literally be stretched out mechanically.
Like you're being pulled through space rather than that space is being pulled.
It comes down to the same effects. I mean, my limbs will be stretched out.
Okay.
So if you would actually fall in, you would actually be stretched apart. Not good for you. Black holes are.
And that effect only intensifies the closer you get to the center.
Yes,
that's why the theory is that if you fall into a black hole, you're just going to get ripped to shreds.
Yes. Ouch. Yeah, that is it's not a nice effect. So now, of course, again, the way that we found this equation now is only for the special case that, you know, we're not too close to the black hole. But the full expression would have the same characteristics. So black holes are really dangerous things. The closer you get, the more spaghetti. This is an actual word in black hole physics. The more spaghettified you get. And and then there's time dilation. The amount of time. If you go through the exercise, but now with time, you find that the amount of time comes to a standstill. So you have the effect that if you would actually go in, your time will come to a stop, and you're being stretched out. So even if you were to step out again, you know your strength here out form, your time was standing still, whereas the time of the rest of the universe had been going on for millions of years. So you come out all stretched out, and the rest of the universe is gone. So it's a sucky situation.
That's weird.
So is it as if you're like a photon, in which like the photon's time also like comes to a stop?
I guess so, yeah. I mean, you could argue that if you are exactly 2m, where your time dilation becomes infinite, right? I mean, the amount of time between two events for you is only 0 seconds, whereas for the rest of the universe it's some finite amount. That means that as long as you are at a 2m radius, yes, the universe to you looks like it always looks for a photon. So if you ever want to know, you know what, I would really, really like to know how a photon sees the universe, well, find yourself a black hole, travel there, stand at 2m and look around. No, really, this is what you will actually see what a photon would see.
Wow.
Poor
Just really cool.
photons.
Yeah, poor photons.
But I don't get that because you said the moment you enter, well, at 2m, you're still feeling something pulling you, stretching,
Yes.
yet time is at a halt.
Yes.
Then what is, because, in our, up until now, we were only studying
How can you
space
stretch
time.
if your time is standing still?
Exactly.
Yeah, okay. That is because the time that is standing still is your time just keeps on ticking. Okay. It's if you compare it to other people's time, that you find that other people's time has been ticking a lot faster.
A lot
Yeah,
faster.
infinitely faster, because the time relation between you and the other person is a factor of 0. Right? So if you would take some other guy's amount of time, multiply it by 0, then you get your amount of time.
Okay.
So your time just keeps on ticking. It's only in comparison to the rest of the universe that is not at this point to the black hole that you see that yours is infinitely slower than the rest of the universe is.
So as soon as you cross the event horizon, like the universe like goes to infinite. Like
Yes,
the whole time of the whole universe just flashes immediately.
Yes, the whole universe, all of it in the whole, throughout the whole future history, future of it will happen to you at the same moment. That also means if you want to watch Game of Thrones, all 7 seasons, what you could do is put your TV here, and you go sit on 2M, and then look outward, yes? Because
now he's saying this as a joke, but he's brilliant. He just said he doesn't watch TV that much because his plan is during retirement. At retirement, he's just gonna sit there and he's just gonna be like, "Yup, seen everything in my lifetime."
I might come back tomorrow and have seen everything. Yeah. Black hole at home. So yeah, it's quite an interesting space-time. This. I don't know how we are on time, by the way. Speaking of time.
5 minutes over.
5 minutes over, okay, then we should stop. Let me make final comment here. Yet again, we can see here why, due to spaghettification, why black holes do not send out light. Because the spaghettification at 2m, again, you would have to do a full calculation with the crappy integral and such, at 2m becomes infinite. You have an infinite spaghettification at 2m. So your time goes to standstill, but your stretchiness becomes infinite. Yeah, that means something. That means that the electromagnetic wave that you would have trying to come out at 2m itself will be stretched out. But yet again, that's another way of saying that its wavelength becomes ridiculously big. Or if you want, the wavelength times the frequency is equal to the speed of light, the c. Well, if one of them goes to infinite, then the other one goes to 0, and you get that your frequency of this electromagnetic wave has gone to 0. So a photon that tries to climb out at 2m will have infinite wavelength, or, which is equivalent, has 0 frequency. So you end up with a photon that is ridiculously redshifted, infinitely redshifted. Now that makes it very black. No matter how you look at it. It's not because your biological eyes are not good at seeing infrared or something like that. No, the infrared is stretched beyond any measure.
So the photon still exists, it just can't be detected by anything that detects electromagnetic
It becomes
spectrum.
almost a philosophical argument.
Yeah.
I mean, does it still
Yeah.
exist? It is infinitely stretched out. Or if you put quantum mechanics in, if the frequency has gone to 0 and its energy is proportional to the frequency, that means the thing has no mass, never had mass, but it now also has no energy. So
What are you looking at?
what is it?
What is it?
Yeah,
Yeah.
It's nothing.
and then it's sort of literally stretched out to nothingness.
So you can say that black holes destroy light, or
Yeah, I think that's a better way of saying it than that they
Yeah.
absorb light. I mean, absorbing light, it gives the impression that something is being sucked in. It's not being sucked in,
Yeah.
it's on its way out, but on its way out it's being spaghettified until infinity and then destroyed into
Does
nothing.
it also get spaghettified when it goes in the black
Yes.
hole?
Yes.
So it's spaghettified twice.
Yes.
The black hole doesn't gain anything from a photon approaching a black hole.
No, it does. But we're talking about a different situation now. Before I was talking about the photon trying to get out, but if you were to shine a photon back in, yes, you're right, that it would also be spaghettified. And then the photon going in is actually giving the black hole some extra energy.
Wouldn't it, before that happens, stretch out to infinity and then have actually
No, that's
energy?
true, but the energy has to go somewhere, right? And
Yeah.
the energy then goes into extra curvature of the space-time, which effectively is the same as if you fed the black hole some extra mass.
So it gets bigger, the black hole.
Yes, but only by a very small amount, yes, per photon.
My question then is actually on his comment of a ray of light being shined in.
Yes.
Is if you kind of imagine it in your head and you see the wave of light traveling, getting spaghettified, but it's light, it's traveling at the speed of light. So how come the black hole can stretch out a point here before this point arrives? I mean, it is the maximal speed of the universe. I don't know if my
I'm
point
seeing a contradiction here.
isn't like the stretching out in our example was that
Yes.
you know because or you said when a human being is nearby, you know, your leg and your head are at different distances, so black hole can attract one point and another, but in a wave of light it's continuous and it's traveling at the speed of light. So
Yes.
how can it occur?
But also the space is like getting stretched out, so I don't know if that answers your question.
Because
So it's
it's
like
like the
both things at
difference,
the same
yeah.
time.
It's that difference between moving through space and like being on space that is stretching out.
Oh,
Ah.
I see.
If you think of it like a balloon, yeah, you draw a line, you stretch it, the balloon and the line stretch out at the same
Oh.
time,
Okay.
like with the same rate, right?
If a photon enters a black hole, it adds mass to the black hole,
Yes.
but the photon by itself doesn't have mass.
No,
From
it's
the
mass
point
and
of
energy
view.
is, it's all
In
the
that
same
sense,
stuff.
equivalent. Okay.
Yes.
I see. Okay. So it's not the
Yeah.
light has space as well,
Exactly.
in which it's
Okay, so. Oh, sorry. Yes.
No. It's kind of a stupid question, but if like energy is mass, then does that mean that photons technically have mass? Like it's a stupid question.
Actually, when I was a student, I actually tried that out. So I thought, well, you know, energy is sort of the same thing as mass. You might as well say, yeah, well, E is mc squared. Which holds for massive particles. Well, it should be gamma there, maybe something. But at the same time, for a photon, e bar times omega. So you know, you would end up with saying something like mass of the photon then would be, what is it? H bar omega over c squared or something like that, right? And when it's very easy sort of back of the envelope sort of reasoning, and then I thought, you know what? If I can now write a photon as if it is a massive particle, then maybe I should be able to calculate its deflection in a Newtonian gravitational field, because now it has mass, so Newton should now also deflect it. So I calculated, use Newtonian mechanics, how much the photon will be zoomed in due to the presence of the Earth, and I actually found the answer of the actual curving in, except for a factor of 2. And later it turned out that other people, it might have been Einstein himself, also made a calculation like this or something like that. I'm not comparing myself to Einstein, by the way, but this was something that I tried and came up with. And then I realized that using this and then applying Newtonian physics is just me applying this part of the metric. But there's also the time part that Newton does not take into account unless you make it come into account. And these contribute just exactly by the same amount.
that's a factor of 2.
That was the factor of 2. So this sort of gives you an idea, and it sort of gives you an impression of that maybe light should be bent inwards due to gravity. But you miss it by a factor of 1/2 because Newton only takes into account this part of the space-time metric. It doesn't take part.
So does that like mean that they technically have mass? Because like how can we say that the photons cannot have mass when like mass and energy are kind of interchangeable?
Yeah, but that's the whole thing in relativity. You can use one, you can use the other. It's sort of the same thing anyway. So
Does a photon curve space-time as it
Just a little different kind of mass.
if you have an enormous amount of photons, they themselves will also curve space-time.
What?
But that effect is ridiculously small.
Yeah, I can imagine.
You know something that was really cool the other day?